In this tutorial, you will get to know about the structure of compiler and what are the functionalities done by it. There are 5 basic steps of compilation. First is the lexical analysis. A character stream is sent to the lexer for lexical analysis, and it creates a stream of tokens. Then syntactic analysis is done by using stream of tokens. Then it's transferred as abstract syntax tree to the type checker for the semantic analysis. Type checker generates an intermediate code. This code is optimized. Then the optimized intermediate code is used to generate the code, which we call as the machine code. In computer science, lexical analysis is the process of converting a sequence of characters into a sequence of tokens. A program or function which performs lexical analysis is called a lexical analyzer, lexer or scanner. A lexer often exists as a single function which is called by a parser or another function. A lexer first scans the input. It removes white spaces. Then it removes comments. Then it manufactures tokens. If there are any errors, it generates lexical errors. Finally, it passes the generated tokens to the parser. Lexical analysis converts a character stream to a token stream of pairs. Why to use a separate lexical analysis phase? Programs could be made from characters, and parse trees would go down to the character level. Lexical analysis is firewall between program representation and parsing actions. A token is a string of characters categorized according to the rules as a symbol. It may be classes of sequence of characters with a collective meaning. It may be constants, operators, punctuation, or reserved words. Lexeme is a character sequence matched by an instance of the token. For an example, sqrt. Here you can see several examples of some types of tokens: identifiers, keywords, integers, floating point numbers, symbols, comments. Some token types have values associated with them. Here are some of them. Tokens are frequently defined by regular expressions, which are understood by a lexical analyzer generators such as Lex. The lexical analyzer reads in the stream of characters, identifies the lexemes in the stream, and categorizes them into tokens. This is called tokenization. If the lexer finds an invalid token, it will report an error. Now, let's see how the implementation of lexer is done. Lexer is implemented with a finite state automation that corresponds to the regular expressions describing tokens. This includes finite set of states, set of transition between states, transition taken on input symbols, one starting state, and a set of final states. Comments and white spaces are not part of tokens. White space includes blanks, new lines, tabs. Only first is relevant, and we can throw away the rest in a sequence. Comments may want to be preserved for printing user source. Lexical analysis can often be performed in a single pass of reading a character at a time. Single pass lexers can be generated by tools such as Flex. A lexer generator, it performs three tasks: taking inputs as list of regular expressions describing tokens in language in priority order, taking associated action for each regular expression. As the process, it reads patterns, builds finite automation to accept valid tokens. As the output, code implementation of finite automation that reads an input stream and it breaks up into tokens according to the regular expressions. Syntactic analysis. What is syntactic analysis? It is the process of analyzing a text made of a sequence of tokens to determine its grammatical structure with respect to a given formal grammar. Wow, how does it done? For that, it performs context-free syntactic analysis. It guides context-sensitive analysis. Then it constructs an intermediate representation such as an abstract tree. Sometimes it may have to generate meaningful error messages. If errors are found, it tries to correct them. Parser is a component in both compilers and interpreters. It checks for correct syntax and builds a data structure. Normally, parsers are programmed by hand. There are some third-party tools as well. When a lexer sends token to a parser checks whether tokens make an allowable expression with reference to a context-free grammar. There are two types of parsers. which is called top-down parsing, and bottom-up parsing. In the top-down parsing, it is attempted to find the leftmost derivations of an input stream by searching for parse trees using a top-down expansion of the given formal grammar rule. Tokens are consumed from left to right. Inclusive choice is used to accommodate ambiguity by expanding all alternative right-hand sides of grammar rules. When we talk about bottom-up parsing, a parser can start with the input and attempt to write it to a start symbol. Intuitively, the parser attempts to locate the most basic elements, then the other elements containing these, and so on. LR parsers are examples of bottom-up parsers. Another term used for this type of parser is shift-reduced parser. Semantic analysis is divided into 4 categories. It is context-sensitive analysis, strategies for semantic analysis, attribute grammars, and symbol tables and type checking. First, let's consider about context-sensitive analysis. The compilation process is driven by the syntactic structure of the program as discovered by the parser. Semantic routines. First, it interprets meaning of the program based on its syntactic structure. Then, it's associated with individual productions of a context-free grammar or subtrees of a syntax tree. Why does context-sensitive analysis is hard? Because answers depends on values, not syntax. There are several alternatives for context-sensitive analysis. That is, abstract syntax tree, symbol tables, language design. Next, let us consider about attribute grammars. Attributes could be added to the syntax tree. They can be added to each node. Then, we have to specify the equation to define values. Then, propagate values up or down. In practice, there are several advantages and disadvantages of attribute grammars. The advantages are clean formalism, automatic generation of evaluator, high-level specification. And the disadvantages are evaluation strategy determines efficiency, increased space requirements, parse tree evaluators need dependency graph, results distributed over tree, circulatory testing. Next, let us see about symbol tables and type checking. Purpose of symbol tables is to keep track of names declared in the program. A symbol table entry associates a name with a set of attributes. Symbol tables include functions. The goal of type checking is to ensure that operations are used with the correct types. This enforces intended interpretation of values. Type checking falls into four categories of languages types. They are statistically typed, dynamically typed, mixed model, and untyped. When we consider about statistically typed, all or almost checking of types is done as part of compilation. In the dynamically typed model, almost all checking of type is done as part of program execution. In mixed model, statistically typed and dynamically typed are both considered. As an example, we can give Java. Languages like assembly does no type checking. It means it's untyped. Type checking is the process of verifying fully typed programs. Type inference is the process of filling in missing type information. The two are different but are often used interchangeably. There are several issues in typing. Does the language have a type system? When is typing performed? How strict are the rules to be enforced? When we consider about components of a type system, there are several. Built-in types, rules for constructing new types, rules for determining if two types are equivalent, rules for inferring the types of expressions. Next, intermediate code is optimized. There are several optimization levels. First one is design level, next assembly level, and the last is runtime level. In the design level, it tries to make best use of available resources. In the assembly level, writing code is done by assembly language, which is designed to a particular hardware platform. In the runtime level, the optimization is done according to an actual input. Next, let us consider about platform-dependent and independent optimizations. In independent techniques, these techniques are generic techniques. Generally, they serve to reduce the total instruction path length required to complete the program and reduce total memory usage during the process. Dependent techniques involve instruction scheduling, instruction level parallelism, data level parallelism, cache optimization techniques, and the optimal instruction scheduling might be different on different processes of the same architecture. Optimizing existing code usually does not add new features. It might add new bugs in previously working code as well, because manually optimized code might sometimes have less readability than unoptimized code. Optimization might impact maintainability of it as well. Optimization comes at a price, and it is important to be sure that the investment is worthwhile. An automatic optimizer may itself have to be optimized, either to further improve the efficiency of its target programs or else speed up its own operation. A compilation performed with optimization turned on usually takes longer, although this is usually only a problem with programs which are quite large. In particular, for just-in-time compilers, the performance of the runtime component executing together with its target code is the key to improve overall execution speed. Next, let's see about fifth step of the compilation. It is code generation. The code generator receives an intermediate representation with supplementary information in symbol table. It produces a semantically equivalent target program. Main task of a code generator is instruction selection, register allocation and assignment, and instruction ordering. Finally, we get the machine code after code generation. That means the computer understands what we meant to be. Well, that's the end of this tutorial. The video production is done by Sri Lanka Institute of Information Technology. Thank you for watching. Goodbye.